Assalamu alaikum, dear students. Okay, last time we were discussing the definition of a continuous function in a topological space. Now, there is a natural question that why we are using such a typical definition. So, today I am going to elaborate that this definition is in fact exactly the same definition, or you can say that we have defined continuity on the similar lines as we have discussed in real analysis. So let's see how the idea we borrow the idea from that typical epsilon delta definition to have this typical definition to discuss the continuity of a function in a topological space, right? So what was the definition? The definition was uh, f from x to y is continuous. Here f from x to y, where x is a topological space with respect to some tau x. It is clear that here is a tau x and here is a tau y, some tau y. F is a function from x to y, where tau x is a topology on x and tau y is a topology on y. We say that is continuous if for each neighborhood v of fx naught in y there exists at least one neighborhood u of x naught such that f of x naught, f of u is contained in V. This was the definition. Last time we have discussed this definition that say this is your topological space x with respect to tau x, and this is your y with respect to y with respect to tau y, and you take a point x and say this is x naught, here is the point fx naught, and you take a neighborhood y, and whenever you take a neighborhood v of fx naught, there must be a neighborhood u of x naught such that this image set is contained in f of u is contained in v. This was the definition. So whenever you take a neighborhood v of fx naught in y, there exists at least one neighborhood u of x naught in x, of course, in x, such that f of u is contained in v. That was the definition we have defined in topology. Now I want to discuss a natural question, that how you borrow the idea of such a typical definition of continuity in topology. I'll try to elaborate that this definition is in fact on the same lines as we have discussed in real analysis. So what was the definition real analysis? The definition was real analysis. F is continuous at a point. F is continuous at x naught belong to x. It is clear that f is a function from x to y, right? If for epsilon positive there exists delta positive such that fx minus fx naught mod is less than epsilon whenever x naught minus x naught mod less than delta. This was the definition in real analysis. For more details and you can see my lecture uh, in real analysis, right? I have discussed the definition of a continuous function in real analysis in detail. So here I just want to discuss that why we are using this definition. Okay, so from here you have idea like fx minus fx naught less than epsilon whenever x minus x naught mod less than delta, and like in that lecture, from here you can have fx belong to fx naught minus epsilon and fx naught plus epsilon. So you can say this is equal to v epsilon of fx naught whenever from here you can write x belong to x naught minus delta and x naught plus delta, right? From here you can write x naught minus delta, and this is your v delta of x naught. So this was the definition. Whenever you take a point from this small neighborhood, its image must be in this small neighborhood of fx naught. This is the neighborhood of fx naught. This was the definition in real analysis. In real analysis, we have defined that this means that if your x is very near to x naught, if your x is very near to x naught, then its value should be very near to x naught, because it's a small neighborhood. We have decided that this is the small neighborhood and epsilon is your pre-assigned number, as we have discussed in real analysis, the definition of continuity, and there I have given details of this definition with the followed by some examples as well. So here delta is also a very delta small neighborhood. So if we plot this definition, we can check that. So what is the definition? The definition is, so I am writing both the definition. This means that fx belong to v epsilon of fx naught whenever x belong to v delta of x naught. Then we say that your function is continuous, where of course this x is a point of your domain of the function. And here the definition was for every neighborhood v of fx naught, there exists at least one neighborhood x naught u of x naught such that f of u should be in v. This is the definition in continuity. Now look at here. If you draw this, what does it mean? You know that you have a function, and you have your x naught, say like this is here, you have x naught, and this value is in fact, this is 0, and this value is fx naught. So you have to decide first the neighborhood of fx naught, because epsilon is your pre-assigned. This is in fact the level of tolerance. So you have to decide your level of tolerance first before discussing the definition of continuity. So that's why first we will decide, say this is fx naught plus epsilon. This distance I am taking, this distance epsilon, and this one is in fact your fx naught minus epsilon. So see this neighborhood v epsilon of fx naught. You have first you have this neighborhood. So here in the definition of continuity, because you have to decide the value of epsilon first, because I am saying that your epsilon is in fact a pre-assigned number. That is, we like to say that this is your level of tolerance, right? So that's why whenever you decide epsilon, in fact you are getting a neighborhood, that is v epsilon of fx naught. So then from here we are generating a delta neighborhood. Like here, these are meeting here and here, right? But we are emphasizing on a smaller number. That's why we will assume that this is delta, and from this sense, this would be x naught plus delta, and like this would be x naught plus delta minus delta, right? So you have this rectangle. This is a small rectangle. Now, what is the idea of continuity now? The continuity says, in fact, you have this. The graph is here, and this is your small rectangle. Continuity says, if you take any point from this neighborhood, you see, then its graph should be here. Graph should be available in this small, it's a very, very small neighborhood. That is, if you read the value is here in this neighborhood. Similarly, if you take a point from here, you see, again, graph is available in this small neighborhood. So that's why you see, again, graph is available in small neighborhood. So mean to say that if I choose even a small neighborhood, very, very small neighborhood of this delta neighborhood as well, if I choose even a very, very small set around x naught, you are choosing some numbers around x naught, then corresponding to these number, graph should be here in this rectangle. So here we are using the same thing, because whenever you are taking any u of x naught, then its image set should be here. If I am saying that this is your u, this is your u, very small u at x naught, this is your small u, neighborhood of very, very small neighborhood u of x naught, because here is your x naught. Then here on the right side you have its graph, and on the left side you have graph. So what does it mean? That its image set is like here, this and this. So this one is, in fact, this is the image set, and I can say that this set is f of u. So f of u is contained in V. So what we are doing? We are writing the same sense in the definition of continuity in topology, that first you have to decide a neighborhood here your fx naught, and you have to decide a neighborhood V. Of course, this is the epsilon neighborhood of f of x naught. Like here, first we have to decide epsilon, and corresponding to epsilon, whenever you decide epsilon, you are getting an epsilon neighborhood of fx naught. So that's why here, corresponding to fx naught, you have to decide first a neighborhood. Means say, whenever there is a neighborhood V of fx naught, there must be some neighborhood corresponding to x naught. There must be some neighborhood u. So this is in fact the u, so that its image set should be in this neighborhood. So like here, your graph should be here, f of u. Okay, I think now it is very easy to understand that why we are using this notion of continuity, because this is a very simple and very straightforward definition, same as we have borrowed, we have used in the definition of continuity in real analysis, right? So see, I can elaborate this again in a better way. So now leave the definition, try to understand the idea. You have this. I just want to microscope my graph so that you can see those neighborhoods on this board. Like you see, this is your x naught, x naught, and I have decided this epsilon. This is not like this, but I just want to microscope. I want to expand to understand the idea so that you can see inside the rectangle what is happening inside, right? So this is epsilon, and here like this is also epsilon. And what is this? In fact, this line is the line of f of x naught. This one is fx naught plus epsilon, and this one is fx naught minus epsilon. And what is this? This is v epsilon of fx naught. So mean, whenever you want to check the continuity at a point x naught, first you have to find the epsilon neighborhood of f of x naught. Here in continuity, in topology, so here is the diagram of topology. So what we are doing in topology, this is your first topological space, and this is your second topological space. Say you have x naught, you're writing it is fx naught, and you have to decide first v. First you have to find a neighborhood of f of x, fx naught. So what we are saying that for every neighborhood v of fx naught, right? So that's why, since you have established, and you may have many such neighborhoods by change of epsilon. If you change the value of epsilon, you are getting smaller and smaller, you are getting different neighborhoods. So that's why there is a concept of more neighborhoods, more epsilon neighborhoods of f of x naught, right? It's so simple. Now, you see here you have this value and you have this value, but we are emphasizing on the smaller. Say this is, if you take this is delta, then again this one is delta, right? X naught minus delta. So this one is your v delta of x naught. Now, if your function is continuous, then corresponding to any of these points, graph should be here in this small rectangle. Then corresponding to, you take any point, this is your small neighborhood. If you take any small neighborhood, if you take any u, then corresponding to u, see, this is your graph. This is your graph, and this graph is in fact, look, this graph is in fact, right? This is one is the set, this set is in fact, now what is this set? This set is f of u, and you see that f of u is lying in v, right? Similarly, if you find a neighborhood x at x naught, then its image set, I mean this image set should be here in v, so this set should be f of u. Similarly, right, if this function is continuous, then corresponding to any point of this neighborhood, graph should be here in this small rectangle, right? Means say that instead of any point, if you take any smaller interval, then corresponding to this smaller interval is in fact those points which are very near to x naught. This is in fact the set of points which are very near to x naught, right? So if you are very near to x naught, you are taking however small neighborhood u of x naught, then you see corresponding this neighborhood, you are getting some function exists, mean you can find graph in this small rectangle even for this small portion. And you see that, if you see that this is in fact the image set corresponding to this small set, which is f of u, and f of u is contained in v, because v was the pre-assigned neighborhood at f of x naught. So that's why here we are doing the same. You are taking fx naught belong to y. If your function from x to y, then you are taking fx naught from y, and you take a neighborhood v of fx naught, then there exists a neighborhood u of x naught, so that f of u is contained in V, right? I think now I have discussed in detail that how we are using this typical definition of continuity. This is not a different sense, right? This is in fact exactly the same sense as we have established in ordinary real analysis sense or in metric space. This is in fact, you can say that the definition of metric space, because you are considering the neighborhoods, delta neighborhood and epsilon neighborhood, or you can say that this is the routine definition of continuity in real analysis, right? So now you see that this definition is not a new definition. This definition is exactly on the similar lines as we have used in uh, real analysis. Now, if this u is not contained in here, this means that this is not subset. Similarly, if corresponding to this u, the graph is not available, it means that you have a break at the graph. Like you graph is here, right? You see that? If your graph is here, then your set must be like one this and other is this. This is your neighborhood. And this is your f of u. You see, f of this was the v and this was the f of u. This is this one your f of u and this was v. So see, f of u is not contained in v because there is a break in the function is discontinuous. So whenever function is discontinuous, your graph is out of this very small rectangle. When graph is out of this small rectangle, this means that the condition that f of u is contained in v may violate for your some neighborhood u of x naught, right? So that's why whenever you find even a single neighborhood u of x naught for which the condition is violating that f of u is not contained in v, this certainly means that your function is discontinuous, just like in real analysis, right? Okay, well, so last time I told you that I'll try to establish a little easy definition because this definition is a little tricky and is a little laborious as well to check the continuity of a function at points turn by turn. So we were not enjoying, in fact, because the definition was a little laborious. You, for corresponding to every point A, you need to find f of a, and then you need to find all neighborhoods of f of a. Then corresponding to every neighborhood, there must be some neighborhood u so that f of u is contained in v. This was the idea. So what we can do that we now can define another definition, which is in fact quite easy and easy to apply as well. So what is the definition? So most of the authors are in fact enjoying this definition, that is I am going to define. But I want to show that this definition is not a different one. This is in fact a result directly deduced from the definition that I have given in last lecture of a continuous function in a topological space. Now, so for that definition, you have a result. What is that result? The result is, you have a theorem, let f from x to y. Of course, here x and y are two topological spaces where tau x is a topology on x and tau y is a topology on y. Be a function from two topological spaces, from a topological space x tau x to y tau y. Then f is continuous. if and only if, then f is continuous if and only if uh, uh, for every open set v in x, we have f inverse v is open in x, v in y, we have f inverse v is open in x. This is very easy, that whenever f is a continuous, you take any open set v from tau y, then you have to check its inverse image, f inverse v, and if this is open in x, mean that this is a member of tau x, you take a member of tau y and find its inverse image. If it is the member of tau x, then we will say that f is continuous. It's a very simple result, right? So you can also write this result as if and only for each subset V open in Y, f inverse, if and only for each, this can also be written as so what is that theorem? F is continuous if and only if for each V belong to tau y, f inverse V belong to tau x. So now this is the theorem. This is biconditional. This means first you have to show this. Again, this one is if condition. You have to first you assume that f is continuous, then you assume that v is a member of tau y, and then you need to show that its inverse image is a member of tau x. This means that v belong to, this can also written as v belong to tau y implies f inverse v belong to tau x. This is in fact the definition. So here v is arbitrary. Whenever you take a member of tau y and find its inverse image, and if its inverse image is a member of tau x, and if this is happening corresponding to every member of tau y, then we will say that f is continuous. So that's why this is in fact if condition. If p, then q. So you have to assume if condition. So here you have two given conditions. One is this, suppose f is continuous, and the second is this, that v belongs to tau y. That is, you have to show that v is an open subset of capital Y, right? So proof. Assume f is continuous, f from x to y is continuous, let v belong to tau y, and you are taking that v as an open subset of capital Y. So you have to show that f inverse v belong to tau x. F inverse v belong to tau x. So this is possible if you can show that f inverse v is a neighborhood of every member of some open subset of capital X, because you can see my lecture number 15. In lecture number 15 we have shown that if capital N is a neighborhood of each of the point of a set G, then G must be open. Then G must be open. Okay. So here the idea is, let V belong to top I. So let assume F is continuous, and you can take, and V belong to top I. You are taking both the condition. So let X belong to F inverse V. This implies if X belong to F inverse V, then of course Fx is in V. Then of course this implies Fx belong to V, and you know that this means that V is an open neighborhood of Fx naught, and F is continuous. So you know that whenever you say that if F is continuous and V is a neighborhood of F of X, then there must be a neighborhood U of X in capital X, right? And F is continuous. So by definition of continuity, there exists at least one neighborhood U of X such that F of U is contained in V, right? Okay, since you are given that F is continuous, and here you have taken some X belong to F inverse U, of course you are applying F on either side, then Fx belong to V. This means that V is a neighborhood of F of X, and since F is continuous, and in our previous definition it was very much clear that whenever there is a neighborhood V of Fx and F is continuous, so by definition of continuity there must be a neighborhood U of X such that F of U is contained in V. F of U is contained in V. But then this means that here also remember that neighborhood U of X, this means that X is a member of U. This means that X is a member of U, right? So this implies U is a subset of F inverse V, and this means that X belongs to U and U is a subset of F inverse V. Okay, look at here. Since X was arbitrary, so this means that F inverse V is a neighborhood of X. F inverse V is a neighborhood of it. And you know that if N is a neighborhood of each of its points, then you know that we say that N is open. So you have, it's a very simple result. It's a simple result that see lecture 15. In lecture 15 I have established that if capital N is a neighborhood of each of point of U, then N must be open. Now since X is arbitrary, so this means that F inverse V is a neighborhood of X, and since X was arbitrary and also belong to U, this means that F inverse V is a neighborhood of each member of U, and since X was arbitrary, since f inverse v is a neighborhood of each of its point, because you have taken x from f inverse v, you have taken x from x inverse v, and x was arbitrary. Since f inverse v is the neighborhood of each of its point, so before this you can write as since x was arbitrary, so f inverse v is a neighborhood of each of its points. So from here you can say that f inverse v is a neighborhood of x. From here you can say that from here this implies f inverse v is a neighborhood of x. And since x was arbitrary, so f inverse v is the neighborhood of each of its points. When a set is a neighborhood of its every point of itself, then this set must be open. Then this set must be open, because an open set is in fact is a neighborhood of its every point, is an open neighborhood of each of its points, right? Hence f inverse v must be open. So this is because of a theorem. I have established that theorem in lecture 15, that if G, any set G is the neighborhood of each of its points, then G must be open. There was a bicondition. G is open if and only if G is a neighborhood of each of its points, right? So that was theorem. G is open if and only if G is a neighborhood of each of its point, right? This was the result. And here see, x belong to u, u is this. What does it mean? This means that f inverse v is a neighborhood of x, but x was arbitrary. So this means that f inverse v is a neighborhood of each of its own point. This means that f inverse v must be open, right? Using this theorem. And we can also establish, if you take union of this is if you take union of these numbers, and this number is in fact from f inverse v. So this union must be f inverse v. This is union of u, and this, since each u is contained in this, so union of this is contained in this. Ultimately f inverse v is in fact union of u. That's why it must be open, because union of u, union of open sets is always open. It is so easy to establish, or you can refer this theorem to write directly. So one thing is clear, that f inverse v must be open. Hence that is f inverse v is an open set in X, or f inverse v belong to tau x. So we have established. Right, this is so easy. We have shown that f inverse v is a neighborhood of x, since x was arbitrary. So f inverse v is a neighborhood of each of its points. And in lecture 15, I have given a theorem that G is open if and only if G is a neighborhood of each of its points. And that's why f inverse v must be open. This means that, you know, that f inverse v is in fact the subset of x. This is an open subset of x. This means that f inverse v is in tau x, right? Now conversely, we can prove its converse. Conversely, suppose for each v belong to tau y, we have f inverse v belong to tau x. Now you need to show that f is continuous. So for continuity, you need to you need to prove that typical definition. What was that? This was whenever v is a neighborhood of fx naught, there exists at least one neighborhood u of x naught such that f of u is contained in v. Now, I need to show this, right? Whenever you take v as a neighborhood of fx naught, so you have to take v as a neighborhood of fx naught. Since v belong to tau y, and of course fx naught is a member of y, that's why this can be considered, right? So idea is so first you take a point x of x and a neighborhood of fx and y. Let x belong to x and you take any neighborhood, you take n, a neighborhood n of fx and y. Let x and n be a neighborhood of fx in y, right? The idea is we are taking some x belong to capital X. Of course, if x is an element of capital X, then fx is in y, and you have assumed that n is any neighborhood of this fx. Then by definition, whenever I am saying that this is a neighborhood, then by definition there is an open set v of y. This is the definition of neighborhood. Again you see the definition of neighborhood in lecture number 15. Then by definition of neighborhood, there exists an open set v belong to tau y. There exists an open set v belong to tau y such that x belong to v and v is contained in capital N. Okay, this is the definition, right? Because you have taken x any arbitrary point, then of course fx is in y due to continuity, because you want to prove that f is a continuous function from x to y. And since n is a neighborhood, so by definition there must be some open set v belongs to tau y. For sake of convenience we are taking v, so that the condition is satisfied. This is in fact the definition of neighborhood. But then if you are doing this, this means that you can write but then sorry, this is fx, this is not this is fx, then this is an open set v of tau y, so that v contains fx. V contains fx. You know that here is fx, here is fx, and there should be v and then n. Then we will that n is a neighborhood of this fx naught if fx is contained in some v, right? I have elaborated in detail in lecture 15 the definition of this neighborhood. So fx, but then what does it mean? This means that x belong to f inverse v, which is subset of f inverse n, like this. Okay, so if you take this f inverse v is equal to u, so what does it mean? Okay, for sake of convenience I can take this f inverse V say this is number 1. So let f inverse V is equal to U, then by 1 we have x belong to U and U is contained in f inverse N. Okay, we are here. This means that f inverse N is an open neighborhood of x in capital X. You know, x belong to capital. Here x is an element of capital X, and you know that this U is a subset of Fn inverse N. So this means that f inverse N is the neighborhood of x in capital X. This means that, this shows that f inverse N is an open neighborhood of x in capital N. Right. Because you know that you have taken V as V was open set and f inverse V is open. You are given, this is given, then U is open. You are given that U is an open set. This is given. Okay. This means that is an open neighborhood x in X, and from here we can write fx belong to f of u, which is contained in capital N. Right? You see the definition? So whenever N is a neighborhood of some fx naught, so there must be some u in capital X so that f of u is contained in capital N. F of u is contained in capital N. Okay, so here you see that what was the supposition? Supposition was whenever V belong to tau y, this imply f inverse V belong to tau x. So that's why this u, from here you can say that u belong to tau x by supposition. This is by supposition. If you take f inverse V is equal to u, this implies u belong to x. This is by supposition, because your supposition was whenever V belong to tau y, this implies f inverse V belong to tau x. So what does it mean? If this f inverse N is containing an open set of capital X, so this implies that this is an open neighborhood of small x in capital X. Right? You can say that. This means that f inverse N is an open neighborhood of x in capital X. That's why now you apply f on either side. Fx belong to f of u, which is contained in capital N. So this implies that f of u is contained in capital N. Hence, what we have established, for capital N, for a neighborhood capital N of fx in y, there exists a neighborhood u of x in capital X such that f of u is contained in, such that f of u is contained in capital N. This implies f is continuous at x, and since x was arbitrary, hence f is continuous. Okay, this theorem was so easy because we were playing with the definition of continuity, and the second condition, that was whenever you take an open set from tau y, we will see that its inverse image is in fact an open set in x is a member of tau x. So now, since there is a biconditional between these two definitions, that's why now you can enjoy this definition. So let's see the last example again. This is now quite easy to use this definition rather than that definition. Okay, so how you will use? What was the last example? So far we have discussed for the definition of continuity. I have written a little bit about the last example. This was x was ABC. I just want to recall x was ABC and tau x was, we were writing to x phi x a c. This was phi x a c. Then there was a b. Then it was a c. This was the tau x. Then you have to choose y 1 2 3. And then what was tau y? This was phi y and 1 1 2. I just want to see the last example that we have discussed in favor of the definition of continuity. Now we want to see that example with reference to this new definition. Okay, so here your function from that we have defined, f from x to y, was f of a was 1, f of b was 2, and f of c was 3. This was a function that we have used in our last example. The ID was 1 and 1 2. Then a c a c a b a c, yes. Okay, now at continuity at x is equal to a, what is the idea? You find its image. F of a is equal to, you know what is f of a? This is equal to 1. And then find open sets which contains 1 here. You find open sets which contain 1. And then find their inverse images. If there is inverse images are the members of this, then the function must be continuous at x is equal to a. So, members of tau y containing 1, that is equal to f of a, are, what are these members? You have 1 1 2 and y. See, this is v is equal to y v1, and you have assumed this was v3, and v2 was 1 2, and v3 v2 was 1 2, and v1 was 1. Now no need to find neighborhoods, and you just take their inverse images. If their inverse images are the members of tau x, then function must be continuous at x is equal to a, and the same is true for all other things. You just find, here we see that f inverse v3, that is f inverse y, and you know that the function is from x to y, So f inverse y must be x. This is equal to x. This belongs to tau x. And f inverse v2, what is f inverse? What is v2? So v2 is here 1, 2. This is 1, 2. What is the inverse image of 1, 2? The 1, 2 is 1 is A and 2 is B. This is AB. This is AB. Yes, this also belongs to tau x. This belongs to tau x. And what is f inverse v1? Which is f inverse of 1. What is this? This is A. And what is A? The inverse image of 1 is f of 1, because here you see that this implies that A is equal to f inverse 1. Right? So A, this also a member of tau x. Yes, this means that f is continuous at x is equal to A. Now you no need to check separately for every members of tau. You need from neighborhood u of A, so that f of u is contained v. This was a little laborious. You just find members of tau y which contains you find members of tau y which contains 1, the image f of A, that was 1. These were the member, and you just take their f inverse image. So f inverse v3 member of tau x, f inverse v2 is a member of tau x, f inverse v is a member of tau x. This means that now it's so easy, and according to our last theorem, you can say that f is continuous at x is equal to A. Similarly, you can verify that f must be continuous at x is equal to B, as well as it must be continuous at x is equal to C. Now conversely, you can see that why it was not continuous when you change the definition. When you defined last time, we defined g from y to x by g of 1 was A, g of 2 was B, and g of 3 was C. Just find the because corresponding 3, you have just one open set, that is y. That is y. That is C. Corresponding to C, you have open sets in X, which are C, AC, and X, right? So we will say that f inverse C, which is equal to 3, and 3 is not here. That's why this must not be continuous. So at x is equal to C, we see that, note, g of C is equal to 3, and sorry, here for x is equal to y is equal to 3. So you need to check y is equal to, for y is equal to 3, that is g of 3 is equal to C, and members of x, members of x containing C are, what are the members? Here C, AC, and then X, or C, AC, and X. Say this is V3, this is V2, this is V1. Now check f inverse V1. Now you see what is f inverse V1? This was f inverse C. And what is f inverse C? This one is 3. This is in fact 3. And there is no open set of the type. So 3 does not belong to tau x, sorry, tau y. This means that this function is not continuous at x is equal to, at y is equal to 3, right? If you take from g from y to x, then this function is not continuous. Yes, this definition is a little easy in noticing the continuity at a point. So that's why now to onward we will use this definition. The definition was, whenever you take an open set from tau y its inverse image should be open in tau x. If this is the case corresponding to every open set of tau y, then we will say that f is continuous from x to y. Right? Now you can compare both the definition, and in next lecture we will try to find some examples of continuous functions, and also we will have few important remarks. Okay, thank you very much. Allah Hafiz.